All right, welcome to Unit 2, Lesson 3 on relative velocity. This is example question number 2. And in this question, we're going to be going over how to solve a problem where we have a boat that we have a known velocity of the boat, and it's attempting to cross a river that has a current in it. Ultimately, we're going to see how much the current affects the direction and the displacement of this boat. Okay, so jumping right into it, we know that this boat from the question says travels at a max speed of 11 meters per second. And that's in still water. So that's from our above formula, the velocity with no wind or current. Next, we have the question telling us it heads south across a 90-meter wide river, which has a current flowing at 6 meters per second towards the east. And our goal is to find the boat's velocity with respect to the ground. All right, so let's break this down a little bit. First off, I'm going to draw myself a diagram because that's a good starting point. So here I'm just going to draw the shore banks. So north and south shore. I'd like to draw myself a little compass. I'll do it in a brighter color. So we have north, east, southwest, because this question has direction. And what other bits of information do we have here? We know that the distance from one shore to the other, we know it's 90 meters. So let's sketch that on here. So this shore to this shore, it's going to be 90. That's at 90.0 meters. And okay, that kind of sets this up. I want to go a little bit slower on how we're discussing the velocities here. So first off, we have the velocity of the ship, which is 11.0 meters per second, and it's heading south across this river. So I just want to sketch that line across the river, and it is going to be going 11.0 meters per second. Okay. Now remember when we were doing our first vector diagrams in a couple lessons ago, 1 or 2 lessons ago, we said that we'd travel and we'd reach a destination and then we'd move again from the end of that destination. We're following the same system here. We're moving one at a time, and we're moving from where we leave off, from the tip. We always draw our next line from the tip here. If we were to draw our next line from the tail, that's not where we left off. That's where we started. And so we're going to have 2 lines coming out of our start point, which doesn't really help us at all. It's actually going to give us the wrong answer. So here I'm going to change the color up. And from the tip, I'm going to draw the second vector, which is the velocity of the water. Okay, so this was 6.00 meters per second. Perfect. Now, what color haven't we used yet? We haven't used green. Okay, so our final vector line, or our net sum, is going to be traveling along this line. And this line, if we solve for its length, will be the velocity. And we want to solve for this angle because when we have velocity, we need direction. So we need to find theta as well. Okay. That, I think, is within our ability range as of right now. So let's start with, I'll go back to blue because it's used there. Let's find the magnitude of this side. This is just going to use Pythagoras theory. So we have a squared plus b squared is c squared. And we plug in some values. So we're going to have 11 squared plus, what was it, 6 squared is equal to c squared. So we have c squared is equal to 121 plus 36 I did way more steps than I needed to for this. So if we do that, we square root both sides. We can say that c is equal to, what do I get? 12.5 meters per second. You could probably actually keep more sig digs for now than what I have, because part B is going to use more. Oh, also keep in mind, this is only part A. Okay, so we have the magnitude, which we solved with Pythagoras. So we know this question mark is equal to 12.5 meters per second. And that makes sense, right? We have this boat moving southward, but it's also being pushed to the side. So it's actually moving across a fast river. So it's going to be going faster than its normal speed. All right, but we can't just have magnitude here. We need direction as well if we have velocity. So let's do that as well. Our angles here, we have an opposite and adjacent, so it's a tan. So theta is equal to the inverse tan of opposite side, 6 over 11. So theta is equal to, I get 28.6 degrees. And let's work the direction out. So here's south, so it's measuring off of the south direction. So it's going to be east of south. East of south. So our answer for A is 12.5 meters per second, 28.6 degrees east of south. And there we go. Part A done. I'm just going to move right into part B because it flows pretty naturally with part A on this one actually. We need to use some info from part A to solve part B. So part B, I'll put up here. All right, and now we need to determine the total distance this thing travels. It's kind of an interesting trick as to how to go about this. The first thing we need to do is, well, we know velocity. We know the speed that this thing's traveling. But distance or displacement, it's asking for distance. The formula for it is distance is equal to velocity times time. And we have velocity, 12.5 meters per second, but we don't know the time. Interesting thing with this question is that we have the y velocity and we have the y distance. So we can say, since we know how fast it's going along the y dimension and how far it goes along the y dimension, we can just do a standard rearrangement of the same formula to find time. All right, be careful with the values you use though. So we're going to do time, little rearrangement, right? We can divide velocity on both sides if we want to show that. So these cancel. So I'll have time is equal to distance over velocity. And our time is equal to the distance in the y direction. So 90 meters divided by 11 meters per second. We're not going to choose the 12.5 meters per second because that's not just y velocity. 12.5 meters per second is a combination of x and y velocities. And the x velocity has nothing to do with how long it's going to take to get from one side to the other. Okay, so over 11 meters per second. And the time that works out to is 8.18 seconds. This is actually like 8.18 repeating. It's kind of a neat value. Okay, so now that we have the time it takes to get from one shore to the other, now we take this same formula, so we'll do it in red but slightly more orange maybe. And so we're going to say distance again is equal to velocity times time. But this time, we're solving for distance, and it's equal to this velocity, the 12.5 meters per second, because we're looking to see how far this thing travels in the time it takes to move across. So we have 12.5 meters per second times 8.18 seconds. There we go. And that works out to 102.27 meters. And if we check our sig digs here, we're only allowed 3. So I'm going to round this down. Distance traveled is just 102 meters. That is our final answer for B.